Okay, I only have 3 examples for you guys today, so it's kind of short because I knew I wanted to budget some time for you guys to do your quiz and stuff. So, okay, anyway, most of the time when we were working with revolutions, we were revolving a solid, aside from the cross-sectional ones, we were revolving a solid about either your x-axis or your y-axis. And we saw a ton of examples where sometimes we had to use disk method, sometimes we have to use washer method. I feel like you guys have that concept nailed pretty well, when to use one compared to the other, right? When you've got any of that empty space that you're going to have to cut out or need to use washer method. But it's a really good idea to try to get a visual on these, okay? On your quiz, like I didn't put any graphs on your quiz, but for sure, make sure you guys sketch a little bit of a graph to give yourself an idea of what's going on, okay? I didn't put any functions on there that would be like, what does this function look like? I think they all should be very accessible to you guys. So what we're going to focus on today is using those same methods. We're going to revolve around lines other than an axis. Could be a vertical line, could be a horizontal line. That line could lie above your solid. It could lie below your solid. But the big thing you guys need to recall is actually something from 6.1 that, you know, we kind of use this concept all throughout the rest of our examples, but it really comes into play here. So we've done a ton of time revolving solids about an axis. In many cases, you can use either shell method or washer method or even disk method to do a lot of these. And I'll try to show you different methods to do each one. But back when we were doing area in 6.1, so when we were finding area, and we did it with respect to x and with respect to y, I put these up here. Like I put these this articulated like formula up here already for you, but I just want to remind you of it because again, it really comes into play today. So when you're doing your integral with respect to x, like when we do disk or washer method, and we integrate, remember your bounds represent your x values from your left x value to your right x value. What's going to change a little bit with what we do today is how this top minus bottom might look, okay? Particularly if I'm revolving something around a line that's above it, instead of my top part being my function, it might be the line that I'm revolving it around. So if it's, you know, like y equals 5 or something like that, you'll find that the first value could very well just be your constant 5. And we've seen some stuff like that before. And then the bottom could be your function, or if that line that you're revolving it around is below, could be the bottom curve as well too. When we did disk or washer method, we had 2 sets of radii subtracted from each other. So you might see this top minus bottom come up twice in the same integral, right? You might have top minus bottom squared for like the full outer radius and the top minus bottom squared for your inner radius as well too, okay, when you're working with like an annulus. And then same thing if I do it with respect to y, then remember your limits are y values and you're doing right minus left, okay? So this is, again, just to kind of get us in a mind state before we face the following problems. So I'll try to do each one using shell and, you know, either washer or disk method, okay? For the first one, this is actually the same example that we did in, like, for the last example in 6.3 yesterday. So I wanted to call this up again and show you another way to do this. So revolve the region under y equals x squared and over the interval from 0 to 2 on the x-axis about the line y equals -1. Solve using 2 methods. Yesterday we did it again by using shell method. So I want to recall that. I want to pull that up here again. And plus it gives us a way to kind of review shell method as well too. But all right, so let's say that is 1. Function looks like that. Yeah, okay, cool. And then we are working with this section here. All right, so it's bounded above the x-axis on the interval from 0 to 2, below x squared. And then we want to revolve it around the line y equals -1. So we'd say -1 is here. So our line's going to be here. Okay. So if I start by using shell method and just reminding ourselves of what we did yesterday, remember our formula for shell method was integral a to b 2 pi radius, should be asking you guys this, times height times thickness. Okay. And then what I said yesterday is when you're revolving it around, when you're using shell method and you're revolving it around a line other than an axis, oftentimes it affects your radius, okay? So again, the way shell method works, we take our cross section actually parallel to our line of revolution, and we're revolving it around and we're creating cylinders, right? Cylindrical shells. So we're doing 2 pi r times h is, the area that we are actually integrating. So again, yesterday this shook out to be integral from 0 to 2. The nice thing is, even though it's perpendicular to the y-axis, we can still do it in terms of x. And our radius is what changed for this example. Do you guys remember what our radius was yesterday? Yeah, because it was y minus -1, right? So we were doing our distance from whatever arbitrary y value we pick, and then also -1 down here. So it was this distance here. So y minus -1 or y plus 1 is what went in for our radius. And then when we do our height, that actually came out of the height of our cylinder, which then we look at our rectangle that we drew within our picture itself. So that's a classic case of when we're using right minus left. Our right value for our height is going to be this bound for x, which was 2, and then our left value was this curve. Okay. Now, since we were doing it in terms of y, rather, I also messed up my bounds. We have to go back and check that. But since we're doing it in terms of y, we remember yesterday we had to take y equals x squared, and we solved it and said x equals square root of y. So square root of y went in there. But then I messed up my bounds. What should my bounds be instead of 0 to 2? Yeah. Okay. So then I think we actually went through and integrated that. And if I remember correctly, it was 120 something over 120 something pi over I don't remember what it was, 3 or something like that. I don't remember. But either way, so that's how we would do it using shell method. Let me show you how to set it up instead by using a different method. So let's talk washer or disc. If I wanted to revolve this solid about that line, which method would I have to use, washer or disc? For sure. You've got that empty space that's in between the solid and the line of revolution, so I'm going to have to use washer method. All right, fine. So remember, that's just integral of pi r squared. In this case, we're going to do dx, okay, because I'm revolving it around a horizontal line. So remember, when you do washer or disc method, if you're revolving it around the x-axis, we do it in terms of x. Since our line is parallel to our x-axis, we're still going to do it in terms of x. The way I draw my cross sections are going to be a little different, okay? So I want to do top minus bottom, since I'm doing it in terms of x, okay? So when I do the top of my outer part, and again, I'm drawing these rectangles just in an arbitrary place, but I would need to connect my topmost part to my bottommost part, which in this case, the bottommost part represents a line of revolution, okay? So my first rectangle I'm going to think of like this. That would be like our capital R of x. So that would, the difference between those two would be my first radii squared. And then the radius that I want to carve out that I'm going to subtract is going to be for the dead space here. So it's going to be this part right here, okay? So when I write my integral, I'm going to keep those things in mind when I think about my radii. So my volume is going to be pi integral. Now my bounds will be 0 to 2 because I'm doing it in terms of x. Okay, so inside of this first set of parentheses, I need to do top minus bottom squared, and it's going to be like the whole outer part, okay? So in that case, it would be my first rectangle that I drew here, or the one that's to the left. The top part of that's going to be x squared. The bottom part of that would be what? So I would do x squared minus this part right here, which would be -1. Quantity squared. And then subtract. Now I need to subtract out the radii of the piece that I want to carve out. So then that would be my second rectangle I drew there. The top part of that rectangle is 0, and the bottom part of that would be -1. So I would have 0 minus -1 quantity squared. dx. Okay, so I'm using top minus bottom in this case. If your line of revolution is below your solid, you'll see that that equation for that line shows up in the second piece when I do the minus bottom in each spot. If you're revolving around something above, then your line's just going to be that first spot instead because you're doing top minus bottom. All right, let's simplify it a little bit. I don't know if I'm actually going to go through and integrate this. I'm happy to do it if you guys want me to do it. But again, the setup is always the most important part here. So x squared plus 1 squared. And then the last part is just going to be minus positive 1 squared. So it's just going to be minus 1 dx. So then you would expand that out. You would get a bunch of pieces for a polynomial, and you would integrate it. You guys want me to go through that? Okay. I am supremely confident that you guys can handle that. Okay? All right, let's do another one. All right, volume of a solid generated if the region bounded by, we've got y equals x and then 2 minus x squared, is in the first quadrant, is revolved around about the line y equals 3. So we're doing another horizontal line of revolution here. All right, let's get our region sketched in here. I think we can get away with skipping by 2s, so we'll do that. See if I and then our other one is 2 minus x squared. So a parabola that opens down, shifted up 2 units. Okay, so then the region that we want, no, I'm going to do this. Would be here. So we want to revolve that around the line, I think we said y equals 3. So here. All right. Talk to me about methods. Try to think through, what it looks like when we draw the rectangles for each one of those methods and which one might be best to do here. There's for sure, right? Really, no matter which method we use, we got a hole, right? Okay, so that means if we use disk/washer, it would be washer that we'd have to do, okay? So if we think about it in terms of washer method, and I do top minus bottom, if I draw my first rectangle in there, again, I need to do the topmost part, which in this case is my line of revolution, and then the bottommost part, which in this case is going to be my linear function. Oops, I went a little further than I wanted to there. So I would have that rectangle, which I would use to revolve. And then the part that I would cut out that Tarun was talking about would be, again, this top part, line of revolution, and then the bottom part of the piece where I want to cut out. I think that's pretty attainable. I don't think that's too bad in order to do it that way. So let's look at what that setup would look like. What would be my limits of integration? Yeah, I'm doing it with respect to x here, and I guess it wouldn't matter if I was doing it with respect to x or y because the limits would be the same. But again, since I'm rotating it around a horizontal line and I'm using washer method, I should do it in terms of x. So I would do from 0 to 1. Okay. I'll toss that pi in front, and then I need to do the difference of my radii squared. Okay, so I want to do top minus bottom of the full outer part. What is the top of it going to be, and what's the bottom of it going to be? What's that going to look like in there? Three minus x, right? Okay. And then what about the part that I want to carve out? Yeah, 3 minus quantity, 2 minus x squared. Didn't really leave myself a ton of room there, but that's what that setup would look like. Some more things you'd actually have to expand out, but definitely something you guys can handle. Okay, but again, setup is the most important part. Okay. Now, let's imagine I did it using shell method instead. With shell method, the way I draw my rectangles is obviously going to be different, right? I would instead do it perpendicular to the orientation that I drew it now. Because when you do shell method, that logic switches. Okay, so that means I would have to draw horizontal rectangles instead. Okay, so if I did that, then they would look like this, you know? But the problem is, what happens when you get towards the bottom of that region? It's going to switch, right? Like if I, here's this rectangle that's incrementing like the top of that region, but as I get to the bottom, when I do like right minus left for my height of my cylinder, it would switch. So I would have to break it up into two different pieces. So that seems very cumbersome if we were to do shell method. Would you agree? Because like again, when I do 2 pi times radius times height, I'd have to split my height into two different pieces. That doesn't seem fun. So in this case, disk method, not disk, but washer method is definitely the only way that I would do this one. Okay. Do you want to see what that would look like if we set it up using shell? Okay. We'll get practice with shell with this last one as well too. But, okay. All right, let's do one more. We can do this using 2 methods pretty easily. All right, find the volume of a solid that is generated if the region bounded by x equals 2, y equals 4, and y equals 1 over x squared is revolved about the line x equals 2. Solve using 2 different methods. All right, let's get our sketch on. All right, so we're revolving it around x equals 2, and that's one of our bounds as well too. Okay, and then bounded by y equals 4 up here. Once you get all these like pieces in there, always make sure you put, if you are revolving it around a line, make sure you put that, some sort of indication in there. Because if I'm drawing a couple of lines, I want to make sure I know which one I'm revolving it around. All right, so then we have 1 over x squared. What's that going to look like, 1 over x squared? With your finger, do you remember? Yeah, I mean, we're only dealing with that part within that first quadrant, right? Okay, so if I plug in 1, I'm going to get 1 as an output. If I plug in 2, I would get a fourth. So here. And then if I plug in a half, let's see, square a half, you get a fourth. So you would get 4 up here. So then our region is going to look something like that. My question to you guys is, where do I shade? Top right or bottom left? The top right region. You guys agree with Ange? Why? It's all about them bounds. That's where it's bounded by. Very good. Okay. Cool. All right, and then we're revolving it around a line that it's fully connected to. All right, that's kind of nice. So let's talk about methods. What are we thinking? I think it's time to do some disk method. We can also do this using shell method. We'll talk about that as well too, but we got to do disk method. Okay, when I'm doing disk method, I'm revolving it around a vertical line. How do I draw my rectangles? Right to left, right? Okay, so something like this. All right, so volume equals pi integral. Talk to me about bounds. This one ended up being a fourth, right? So this was a height of a fourth right here. So we're going to do from 1/4 to 4 for my y values. Are we cool with that? Okay. All right. And then I have to do my radii. Remember, I guess I just have to say radius. So again, I use my rectangle to help me figure that out. Right minus left. What's my right piece? 2. What's my left piece? I got to figure that out, right? What's that look like? One over square root of y. Cool. Quantity squared dy. That setup's not bad at all, right? I mean, it's really nice when we're doing disk method. It's been a minute since we've done that. You guys are going to get some practice doing that today. And that's another reason why I wanted to do this, because we saw, you know, each one of the methods. We can also do this using shell method as well, too. Let's do it using shell method, just for the love of the game here. Okay, that's going to change the way in which we draw our rectangles. So I'm going to erase our rectangle here, and then we're going to put a new rectangle in. The nice thing, I mean, disk method, in my opinion, like for that one, was pretty simple. The nice thing about doing shell method, like one benefit of doing it is I'll be able to do it with respect to x now, so that's kind of nice. There you go. Just plug that gap there. All right. Okay, so when I draw my rectangle now, I'm going to take my, my strip, my rectangle here. Could have drawn it anywhere within that region, but I just need to draw it there. And again, that's going to help me figure out my my height. Okay, so then integral, I'm going to toss 2 pi out in front. What would my bounds be? I would use my x values now. What x values would I use? 1/2 to 2. Okay. All right. Talk to me about radius. When I do my radius, it would I mean, this you would actually think about a horizontal rectangle in this case for your radius. If we're thinking right minus left, since we're doing it in terms of x, your right part of your radius would be your x value that you're revolving it around, which would be 2, and then minus whatever your x value is, whatever your arbitrary x value. So that's what's going to go in for your radius is 2 minus x, okay? If your solid of revolution was, or if your line of revolution was to the left of it, then instead you would do x minus whatever that line of revolution would be. All right, so again, this is your, this rectangle will give you the height of your cylinder. Your radius, though, that you're revolving it around the line is by, we have to do right minus left in this case, so we would do that line minus our x value. What about when we would do our height of our cylinder? What's that going to look like? This is where top minus bottom comes into play. So what would our top part be? 4. And then minus the bottom, which would be 1 over x squared dx. Easier to do disk. Would you agree? Yeah. That's always the way that I've taught it in the past is, I just have my kids focus on whatever the easiest method to do in this case was, and disk method seems far easier to me. Even like when we did, this is just me, but like, this example is kind of biased, but like, we didn't even attempt shell method because we'd have to break it up into 2 different sets. Like just doing washer method was the way to go there. You'd have to tell me what you guys think about example 1, which method you believe would be easier. But again, I think washer method's easier to do. But shell method wasn't bad for that one at all. I mean, we did that one yesterday. So, all right. Questions there? Okay. All right. I didn't give you guys a ton of problems on your homework. So 4 in the first and then 3 in the second. So, are you ready for the quiz? Do you want me to give you a practice problem real quick before we get into it? A minute to review? Okay. I'll give you a minute to review. I had an AP problem that was really good that I've used on my students in the past that I was going to put on the quiz, but I decided against it. I just made a bunch of individual problems anyway. So, all right, I'll give you a minute or so to review. Grab a calculator. You know you're going to need it if you don't already have one.